Now we'll look at a concept called mutually exclusive events and also how to use Venn diagrams to help us with some of these problems. The definition of being mutually exclusive are events that cannot happen at once. Some examples of this might be picking a card that is a face card and a 7. You can't pick a card that is a face card and a 7. It just doesn't happen that way. They're either face cards or they're not face cards. An example that was given in class was making a free throw and missing a free throw. You can't do both of those at the same time. But there are two events, two outcomes that can't happen at one time. So here we have a Venn diagram with probabilities in here. Notice that if we add up all of these probabilities, in addition to the 0.57 out here, those add up to 1. The meaning of the 0.01 is that's the probability that the person's string breaks and that there's a pop quiz and that their team loses. So there's a 1% chance that all three of these unfortunate events happen on the same day. The 0.03 represents the probability that the string breaks and the team loses, but not a pop quiz. We can't just say that the string breaks and the team loses because that would include all of that. It would be a total of 0.04. The probability of either a pop quiz or the team losing, that will be any event that is inside the pop quiz circle or any event that is in the losing team circle. So what I have to do is add up all of these probabilities and I get 0.39. The probability of not B, not Q, and not L, meaning the probability that the string doesn't break, there's no pop quiz, and there isn't a loss, would be this probability that is not in any of the circles. So this is equal to 0.57. One thing to note here is the probability that the team loses is just the sum of all the numbers in this circle, and that would be 0.28. The probability of getting a pop quiz would be the sum of all the probabilities in that circle. That would be 0.16. We'll keep that in mind for something in just a moment. But the rule for adding mutually exclusive events, finding the probability of one thing or another, or telling us that we need to add. So I want to come back here and look at this. The probability that they lose or have a pop quiz, that says that we should just have to add together the probability of a loss and the probability of a pop quiz. And that is 0.44. But one thing to notice here is that probability of a loss or a quiz is exactly what we were finding in part C. And these numbers don't agree. And the reason they don't is because that one's wrong. Looking at this definition for the addition rule, it's for mutually exclusive events. In this Venn diagram example, all three of these are not mutually exclusive. None of them are mutually exclusive. They all overlap in this Venn diagram. But we can generalize an addition rule for any pair of events. The probability of N1 or N2 occurring can be found using this formula. We subtract because some things got counted in both groups. Some things were in that overlapped region sometimes. So we'll look at two examples, one of which is mutually exclusive, the other one is not. So we're going to pick a king or a 7, so I'm going to be adding two probabilities. There are 4 kings out of 52 cards in the deck, so the probability of picking a king is 4 out of 52. The probability of picking a 7, well, there are 4 7s out of 52 cards. And picking a king and picking a 7 are mutually exclusive. There are no kings that are also 7s. So this is 8 out of 52, which reduces to 2 over 13. Probability of picking a 7 or a spade. Probability of picking a 7 is 4 out of 52. Probability of picking a spade is 13 out of 52. But there are some 7s that are also spades. This is not mutually exclusive. I have to subtract something at the end of this, because the 7 of spades pretend that's a spade, that got counted in this group and this group. It got counted twice. We have to subtract off the probability of picking something that is a 7 and a spade. Well, there's one of those out of 52. And this would be 16 out of 52, which reduces to 4 out of 13. We can easily see that the probability that a rolled die comes up a 3 or a 6 is 1/3. Probability of 3 is 1/6. Probability of a 6 is 1/6. 6 or a 3, we add them together and get 1/3. What's the probability that a die will come up 3 or 6 on the first or second roll? Let's first do this using our addition rule. So probability of getting a 3 or a 6 on the first roll is 1/3, plus the probability of getting a 3 or a 6 on the second roll is 1/3, but it is also possible that we might get a 3 or a 6 on both rolls. So this would be 2/3 take away. Now, probability of getting it on the first roll and the second roll, that would be 1/3 times 1/3, and meaning multiply. So we have 2/3 take away 1/9. That would be 6/9 minus 1/9. Probability is 5/9. Notice that we can't just add together 1/3 plus 1/3, because it's possible that we get a 3 or a 6 on both rolls. Now there's another way of looking at this through the use of a tree diagram. So when we roll the dice the first time, we'll either get a 3 or a 6, or we won't get a 3 or a 6. We'll get something else that doesn't fit with what we're looking for. And if we get the 3 or a 6, we'll stop. If we don't get the 3 or a 6, we'll roll the dice again, because that's what we want. And on this roll, we'll either get a 3 or a 6, or we won't get a 3 or a 6. And we can take the idea from the last section and put our probabilities on these tree branches. Probability of getting a 3 or a 6 is 1/3. Not getting a 3 or a 6 would be 2/3. And now we look at the different paths that get us what we want. This branch gets us the right thing. The total probability there is 1/3. Or we could take this branch going down through the not 3 or 6 and then get a 3 or a 6. And using our skills from last section, we would multiply those probabilities. 2/3 times 1/3. And now we can simplify. 1/3 is the same thing as 3/9. And you see, doing it this way, we also get 5/9 as our probability. What we've just looked at with this tree diagram is actually the complement. It involved the complement of our event. The complement of it raining out is that it's not raining. In the last problem, we looked at getting a 3 or a 6 as the event. Not getting a 3 or a 6 is the complement of that. And if the probability that it rains is 0.3, the probability that it doesn't rain should make sense that that is 0.7. And what we're doing is we're taking 1 minus that probability. We're following with this formula. The probability of not A, or probability of A's complement. This apostrophe means we're talking about that thing's complement, is equal to 1 minus the probability of A. And that's what we used in our tree diagram. We found the probability of A, in this case, probability of getting a 3 or a 6, was 1/3. The probability of not getting a 3 or a 6, the probability of A apostrophe, is 2/3. And now we need to make a Venn diagram to describe this situation. So if we take a minute and read through these 5 things, we see that there are 3 events. So I'm going to draw 3 circles. And what I'm going to start with is actually the 5th one. O and B are mutually exclusive. And what these circles are representing is that someone is in band, someone is in choir, and someone is in orchestra, and everybody is in one of these 3 things. If B and O are mutually exclusive, that means that they don't overlap. So in these spaces, I need to put 0%. Because there can't be anybody that is in both of those circles. That intersection has to be empty. Another way to draw this would have been to take one of these circles and moved it like this. Now they're not overlapping even in the picture. But most commonly you see Venn diagrams that have 3 events drawn as 3 overlapping circles. So that's why I'm drawing it this way. Now, the probability, I'm going to jump up to 3. The probability of C and not O and B is 0.1. Well, that means that everything in C that also isn't in B and O is 0.1, so that would be this region here. Clue 2 says that everything that's not in O has to total 0.6, which would be those three regions. And since 0.1 is in the big top right one, that means that these two have to be a total of 0.5. I just don't know how to divvy those up yet. Clue 1 says that B or C must total 0.8. So everything in B or C has to add up to 0.8. So I have 0.5 between these two regions, and another 0.1 is 0.6. So that leaves 0.2 to go in that space. And at this point I can actually fill in what the big part of O is, knowing that everybody is in one of these three activities. So far I've used a total of 0.8 of our probability. If the entire probability has to add to 1, that means this has to be 0.2 also. And there's one clue that I have not used yet. And that would be that O and C are independent. If they're independent, that means that the probability of O and C is equal to the probability of O times the probability of C. That's our multiplication rule from last section. The probability of O and C, I know that already from my reasoning in clue 1. This orange part is 0.2. I also know the entirety of O. The probability that someone is in an orchestra is a total of 0.4. Now I can use this multiplication formula to figure out what the total probability in choir needs to be. I'm going to divide by 0.4. The probability that someone is in choir is 1/2. In this problem, it would be more applicable to think of it as 0.5. So now I come back to my choir circle. And I've got 0.2 in there already and 0.1 in there already. So that's a total of 0.3. I need 2/10 more to fill me up to a probability of 0.5 in that circle. And then that leaves 0.3 to be just in band. These are a lot like logic puzzles. And sometimes they take a little bit of thought and remembering all of your rules to come up with the right combination of numbers.